Hello and welcome to 23rd lecture of course on data-enabled tribological engineering from experiment to predictive models. The topic of this lecture is Introduction to Machine Learning Algorithm. It's a very interesting topic and the whole course is moving around machine learning algorithms. The first question comes, what is the really requirement? I'm going to express everything from tribological point of view. There will be number of lectures available online. They may have given different kind of requirements, but what I'm going to pose a requirement is only from tribological point of view. So what we say here, using tribulated friction coefficient to solve any mechanical design or failure analysis problem by ignoring system dependence of frictional behavior must be avoided. Reason being, most of the time design we use a coefficient of friction picking up from a literature, which I believe is not going to be right thing, because coefficient of friction is a system dependent and we need to have a sophisticated model to incorporate system dependence. If we are not incorporating, whatever do we do, results may not be correct, or it may require many more iterations, many more experimental readings to come up with the right results. So that's why we require a machine learning to help us. So let's take example. Now I am taking this complete data from a book that's called a tribology handbook. This tribology handbook has a number of data and it is also available online in PDF. You can download directly. This is in the digital printing in 2001. Now this book contains a lot of data. What are those data? Let's see the low friction. For the low friction, bearings have been divided in different manner. We say type of the bearings. Bearing can be rubbing bearing, can be porous bearing, can be rolling element bearing, can be rubber bearing, can be strip where the deflection will help, or knife edge pivot also. So different kind of bearing have been given. Now here we are saying that how do we achieve a low friction? So it's completely related to the tribology. Now what has been mentioned, it will provide a good results with the PTFE. Now question comes, on what basis I'm saying this? If we take this as a data and many more other data, then conclusion can be made. We can reject it, we can give a lot of weightage, or we can say it is only for one situation, but that need to be documented properly. So this is a one. Now second, the for porous it is a good, then very good, elastically stiff, excellent, very good. How do I classify this data? How do I utilize this data? That is a big question. Now take another example. You say carbon graphite coefficient of friction will vary from 0.1 to 0.25 in dry condition. When carbon graphite is used with a metal, it will coefficient of friction will vary 0.1 to 0.35. It's a 3 times variation in the magnitude of the friction. How do I believe it? Which one will going to give good results to us? Now graphite impregnated metal gives a lesser coefficient of friction. Why and how? Because we want to innovate and we need analysis. We really require a quantification in terms of model. And then if it is a grease lubricated, the coefficient of friction drops down to 0.02. These are very good data, but we really require to implement. How do we implement without any quantification? Just by picking up this data, will I get a good results? May not. Now coming to the graphite thermosetting resins, another material change, coefficient of friction varies from 0.13 to 0.5. Now here the instead of polymers or maybe carbon graphite, we are using a thermosetting resin. Why it is increasing coefficient of friction such a high level? We need to have some understanding. Similarly, other cases also. Now in a third table which will show the clutch facing material, we are trying to find suitable material from clutches. Here the coefficient of friction needs to be on higher side because we really require mechanical transmission. Now here the materials have been given for light duty, for medium duty, for heavy duty, for all immersed cases. How do I utilize this? Actually need to be connected with a proper function or proper relations, but whether those relations are sufficient to adopt or to take this kind of readings, or it is just another, we have documented, we have made up a book, and then we are providing some guidance, but that guidance is not complete. So the data utilization will not be significant. So even though there is a lot of literature available, but not in a proper format, it's not usable form. There may be any reason for that, but there is a possibility we should be changing, or we implement, or we come up with some framework where these data can be utilized in much more meaningful manner. Let's take another slide. We say where data utilization. We have already learned something like a running in. We have also learned something about a steady state. But this is a only kind of a qualitative data. It's not a quantification has been done. So are these data available for every material? So when we start looking from that angle, we may get a much more information. And this way clearly says the running in. Now question also comes. Many times people say when you are using oil, running in time will be much higher compared to dry case. Then how do I go ahead? How do I really come up with the proper way? So these are the important aspects to consider. Now this also been picked up from a tribology handbook. This also been picked up from a tribology handbook. Now here it is being given allowable wear depth. What is the meaning of that? We need to go ahead with this much thickness of the coating, or some sort of hardening, is something like a surface hardening or case hardening. So we say that for good quality carburization, the depth comes up something like a 2.5 meter. Now, in absolute sense, I don't make any, I don't find any sense of this. It has to be related to something. Now, instead of carburization, if you go for the nitriding, it is a 0.25. Now, coming to the cyanide hardening, whether shallow or deep, the value is very significant change. The shallow case is a 0.025. In what cases it will be useful? 0.25, which cases it will be useful? Now coming to the white metal, which was used as one of the major material, we say up to 50% of original thickness. So we really required model quantification by setting this. Quite possible author has done number of experiment, and he has put in form of the tacit knowledge that need to be quantified properly. Now coming to the Michael Ashby's book, which has been published on the material selection for mechanical design, you can see he has given the curve between the wear rate constant. We already studied, we say the wear rate can be given in two terms. One is a dimensional and another is dimensionless. So in this case he has expressed in a dimensional form, and then the curve has, the plot has been given hardness versus wear rate. And then here you can see there are lines available which says a Ka, that wear constant, into H, and then these are the line at 10 is to minus 8, 10 is to minus 6, 10 is to minus 4. So it gives the impression that we want a minimum to minimum K. So people may choose 10 is to minus 8 1 car, but alloy steel and all is giving a 10 is to minus 4. So there may be confusion. Somebody start thinking about this K into H, whichever is the minimum, I should go ahead with that. No, that gives a little wrong information. Reason being, the hardness of the polymer will be always much lower than the metal. What's the magnitude? That means this data need to be added with some additional data on hardness to make much more sense to us. So this is important for us. We cannot really, because data are available in literature, but we are not able to use in as it is format. We really require slightly different way to interpret the results, to compile the results, to come up with some algorithm which can really provide us much more meaningful data. And that's why my question comes, what should we do with this information? Whatever information has been provided in a different kind of books, different kind of handbooks, what do we do? Is it only the guidance, or more quantification is possible? In my view, quantification is possible. So I can say, as per my understanding, tribo elements are fundamental components found in virtually all mechanical systems, and tribology is essential factor in assessing the reliability, longevity, and energy and efficiency of various systems. Engineers have successfully implemented several enhancements. However, These enhancements have been limited to few books presented in either in graphical form or tabular form. The generalization of such factual knowledge has not been achieved, probably due to interdisciplinary nature of the tribological knowledge, which already requires a material science, mechanical engineering, chemistry, physics, maths. Now on top of that, we say now computer engineering also, computer science also, data analytics also, and AI also. That gives a kind of so much knowledge is required, so maybe people don't worry. We say that we cannot explore it. However, we know that there is AI algorithms are available and MATLAB software has a many things availability there. So, are we able to put our maybe say knowledge, put it in a proper form? Can we really come up with something better? That's why this kind of course has been introduced. So, what we say, our aim is to examine necessary component of computerized tribology information and data system, as well as provide potential approaches for its successful implementation. So, it's not only the exploration of the data, but how do we implement? So, there are a number of books which are providing data, providing the graphs. We need to come up with something, how do we really successfully implement in a computerized tribology and information system. In my view, this kind of approach will be highly beneficial in the design field, material selection field, as it's going to facilitate dissemination and exchange of knowledge. Knowledge is enormous, but we need to compile, make it much more meaningful so that we don't really require too many experiments. We can use daily data analysis in appropriate manner and come up with a good results. So I can say machine learning is a data driven analysis. We have a lot of data and we are trying to make a model which can learn from acquired data, refine itself to find correct answer and make decision without human intervention. So when we want little more automation, no subjectivity, because we know that when human intervention comes, subjectivity will come, some sort of biasness will come. We want to get rid of those things. We want something, it should be like artificial intelligence and comes in a proper way to give a tribological data in much more meaningful way, in much more useful manner. So let's start think about the tribology on relation between machine learning and tribology. We can say from history point of view, in 1958, Rosenblatt has developed first machine algorithm, and perceptron is a name being given. Of course, you can explore all this in the literature. I don't want to really go through all those things. But I know that ongoing advancements in computational capabilities, as I say that now MATLAB has inbuilt complete machine learning algorithms, and we can utilize it much easier manner. Only we need to put slightly more data in that and try to filter out. Use some of our tribological knowledge in a better manner so the overall results come out to be more useful manner. So we can see that in computational capabilities, machine learning algorithm have gained ability to utilize existing data for model training. That's a new thing. Validation and testing. Often books says that training and then validation, and in some books says only training. Or like we have COFIT methods available from years, an optimization method for the years. We mostly go for the training side. Now here we are coming with the validation and we are going for the testing also, so that we can recognize patterns, we can provide predictions. Most of the time we are trying to give judgment based on a existing thing. We are not going to predict, and then if we are predicting also, we are not going to test it. So that is we are missing. Our testing purpose mostly we do only experiments, and if you do experiment in different labs, quite possible different parameters will come out and maybe different results will be there. So this is what we say, if you can go ahead with providing a prediction and enhance the performance effectively. So that's where the machine learning comes. Now from literature, again many things are available related to the machine learning. I'm not going to go ahead with each and everything. However, I say that broad classification of machine learning algorithm. There is supervised learning and unsupervised learning. What are the processes? We say we have a classification process, we have regression process, we do a clustering, and we do a dimensionality reduction. So this dimensional reduction is very important. If you go through literature and then maybe say even quotient of friction, 5 different authors, and then you find some place, some when the one material composition has been more utilized, some lubricant has been more utilized, maybe somewhere texturing has been given more weightage, somewhere something else has been given more weightage. So when you come up, how do we go ahead? So we try to model all those together, and then we say what is the relevance. We try to minimize the dimension. That's what we can call as a dimensional reduction. And principal component analysis is what a name has been given, and is again available in MATLAB, again widely used. However, in this literature, what we picked up, they use the word PCOA. I don't prefer to use this one, and we will be using word as a PCA, principal component analysis. We don't use a PCOA, right? And then of course there are a number of algorithms available. Again, luckily, maybe say almost 30 to 40% algorithms are available in MATLAB. So will try to give some sort of initial input. More details are available already in the literature. We don't want to go through each and everything from a machine learning point of view. We want more an implementation point of view. So what if I try to express in my word, I say there are mainly two type of machine algorithms, what we say supervised learning and unsupervised learning. However, sometimes we say that semi-supervised learning people have been utilizing, or reinforced learning people have been utilizing. So these are the important. Sometimes people say no, it's not two, it's a four. Four division is supervised learning, unsupervised learning, semi-supervised learning, and reinforced learning. It's up to them, but we say majorly the two, supervised learning and unsupervised learning. Again, we say the supervised learning encompasses the two distinct methodologies. One is a classification, or we are talking about the pattern recognition, and second one is the regression. Coming to regression, as we have been mentioning again and again, that we need models. The regression models are utilized to produce a prediction regarding the numerical values or continuous outcome. Just for example, we want to find out the wear rate of a substance, and for the one system case, so naturally we require system parameters. For a number of system parameter, we can estimate the wear rate using the model. So that will be the regression model. If similarly, we can say regression method can be employed to predict the coefficient of friction, even the film thickness, the temperature rise. So there are so many parameters when the regression analysis can be utilized. That means we will pick up the data from literature, and we will try to make a regression model out of that. Coming to classification model, many times we say, oh, what kind of mechanism of the wear? Is it abrasive wear, or is it adhesive wear, or is it fatigue wear? So this is a classification. Similarly, type of the surface finish is a parallel, perpendicular, maybe diagonal. So we require type of surface finish. We require oil types, oil grades, or some sort of lubricant additives. We are not saying that what should be the percentage of graphite. We say graphite percentage maybe 0.1, 0.01. That is quantification, that will come in regression. But here we are talking classification. So we record both. If we record classification, we record regression, both the cases. Now coming to the goal of the unsupervised learning, again we say the pattern recognition is very important. Group formation is very important. When we have 1,000 data, and then we are trying to come up with a unsupervised learning to cluster in a manner, so more useful information comes to us. So out of 1,000 data, maybe say, oh, 50 data are only useful. So we use a dimensional reduction and then clustering, and so that overall first phase, this is unsupervised learning. So the subsequent we can go for the supervised learning. Again, our emphasis mainly will be on a supervised learning, because that's going to give us a model. While unsupervised learning can be initiated, we can start because available data are too many, and then slowly we move to the supervised learning. So this is what we really require for our course. Now there are I say that in other cases we do have also many other parameters. Sometimes we require a Hudson contact size, sometimes tensile stress or tensile strength, or something like a friction force overall, or maybe some sort of lubricant property like viscosity measurement or viscosity temperature relation. So again, these are all a type of performance parameters to predict the useful life of a product. We know that product will be continuously getting degraded, and we want a useful life or remaining useful life. So in that situation, we really require sophisticated mathematical models for all relating to all these variables. One classical approach has been use a partial differential equations with a number of assumptions. other in approach which we are usually using for this course is something like available data, come up with some sort of a model and predict, and then maybe possible use some sort of a future experiments or maybe on in situ experiment to come up with the right results. So what we can say, machine learning focuses on the development of algorithms and models that enable computers to learn from a data and make prediction or decision. The model acquires knowledge about the relationship between input and output from a provided training examples. So we do have a training example, maybe like we have a number of data. So what we do, we say maybe say some the data will be used only for the training to make a model. Then we think about a validation. Then we think about the testing. So this is important for a prediction point of view. Earlier, this kind of approaches were not utilized. Earlier, we were using kind of curve fit, whatever the data, we fit it and then get results. And the major issue was that time overfitting. And means next time whatever I get input or some other data, I'll not be able to utilize the relation, or relation will not be suitable. Or maybe even one additional parameter comes, I have to restart everything from scratch. While in this case, data augmentation is possible, we need to come up with a slightly different model using a similar kind of algorithms. So what we say in our case, our more interest is to find out coefficient of friction, wear rate, optimize lubricant, maybe say designing a lubricant, maintaining environmental sustainability, and anticipate some maintenance requirement. Therefore, by implementing machine learning with appropriate tribological knowledge, resource efficiency, energy efficiency, renewable resources, weight reduction, longevity can be achieved. In my view, machine learning future holds significant potential in tribological discipline. So we should learn this course and effectively implement this course. Now, again, I picked up this figure from a literature. I found it interesting. We say that classically empirical tribology, many times even people say that tribology is empirical. You say some data, that's all, no meaning, no basis. However, 1960 onward, we brought some sort of science in that. We try to give a relation. After that, because of the computers, we use a sophisticated model, but again, partial differential equation, solving equations, giving some sort of assumption, and one assumption changes, again you need to start from scratch. That was a drawback. Now this is what we are coming in the current domain. We say we are in the domain where AI and machine learning are going to influence, so come up with information science based on their big data. That's what evolution or evolution of the tribological research happens. So I like this diagram, and I picked up and say, no, this is a trick. We started from empirical, then scientific, then computational, now information based. That's what we really require. So what we can say here, establish a new correlation. Quite possible, whatever the data we are learning, whatever relation we are learning, we can establish new relations also, new correlations also. So establish new correlation in a tribological data to predict and control better tribological behavior of the system. It started in 1960 from scientific manner. Still, we have a lot of frictional losses, a lot of wear losses. To really increase performance, or make the tribological performance better, we need to implement this kind of information science based, which we can learn from big data, available data. That's very, very essential. Now here I am also saying, if possible, include macro and nano scale roughness. So data may be available, and now we are learning also that roughness plays a major role. Quite possible earlier data, they don't have a surface roughness data value. So can I really virtually create some surface and think, yeah, this model is suitable maybe because of this surface roughness? May not be absolute correct, but it will give a lot of learning to us. So that's what we are saying. Can you bring those things, maybe use a data topology in this manner? And then quite possible, when we do this kind of churning, this kind of action, computational modeling, we will be able to consider new things like what will be the design, lubricant, coating, which can provide optimum performance to us. So this is what can be achieved using this kind of thing. So let's start what we have used a word classification, regression analysis. What is a regression analysis? Again, I say it's a very, very common thing, has been utilized in the in a literature in a massive manner. Earlier we used to call a curve fit. We get a number of data. You are able to see that this blue color data we were able to get from experiments, and then we say what is a curve fit, what is the really curve, what is the behavior, what is the model. So here the polynomial model has been utilized and one exponential model has been utilized. So this is a curve fit model which will have a utilized earlier. So what we can say, regression analysis can be seen as a specific type of curve fitting. I'm not criticizing machine learning, I'm just trying to compare that people who are familiar with the curve fitting, and then what difference has come in a machine learning. That maybe if somebody is very good or familiar with the curve fitting, how he relates or she relates with this. So what we say, both involve the process of finding a mathematical model in the machine learning as well as this both, and best describe the relation between the variables. In both the cases we do kind of optimization to find out the best relation and then maybe minimize the error. That's both the things. However, the overall goals are slightly different. Best fit, we say that it is for the available data. We are not thinking for the future point of view, and we are assuming it will work, and we are not really thinking from a testing point of view, from validation point of view. And while in machine learning we do, that means suppose we have 100 data regression analysis which would be curve fit method which have been utilized, we use all 100 data. And while in case of machine learning, quite possible for training this model we use a 70% data only for training, and 20% for the validation, and 10% for the testing. Of course, it varies different approach to other approach. Every scientist, every author has a different way to achieve. So this is possible. Now, what is the major issue? When we go for curve fit, we really need to think it should not underfit. Sometimes people use that it should go high polynomial data, 4 level, 5, 6, 7 something. So they go for overfitting. Naturally, now new data comes, it will not really fit in this kind of algorithm. So this is what we call overfitting. So we don't want overfitting, we don't want underfitting. We want kind of a good fit which can really predict proper things. Now we say the primary goal of curve fitting is to find mathematical functions. Same thing in machine learning also, that closely matches a set of the data point to represent the underlying pattern and trend. Up to this level same, but we are talking in a machine learning future prediction, while in curve fit we don't do that. However, now the new curve method is also coming, new algorithms or maybe new software also coming. They have incorporated this indirectly, but maybe it's good when we get inspired from machine learning and implement. But now in machine learning, what we are going to do, we'll be doing some sort of validation, some sort of testing also. So what we say, curve fitting may involve a variety of mathematical function. We already shown this is a polynomial, this is exponential. Same thing here. It can be linear, can be quadratic, can be exponential, can be logarithmic, or any other complex function also. So we try to do a regression modeling and then we try to include a number of mathematical functions. Again, as I mentioned, that in regression curve fit method, mostly we use all the data, all the basically to train. We don't do validation, we don't do the testing, while in machine learning we do those kind of things. So that has been shown here. In particularly machine learning related, we try to find out the model, we use a training set, we do the testing set also. Now here the validation is missing, validation can do the validation also. So what we say, the regression analysis is a statistical technique used to quantify relationship between the one or more independent variables. Here you can see X is an independent variable which can be named as a predictor. Predictor is a prediction kind of thing, and then dependent variable which is a Y, in this case Y is a function of X. We are trying to figure out that. So to understand the strength, what will be the strength of the relation? Quite possible this comes to something, a line is straight line, then actually Y is not dependent on X, or if it depends, it's very weakly dependent, that's a strength. If however if it goes in exponential form or logarithmic form, then we will try to predict that one. So that's what the prediction comes. And then we say it makes a prediction and infer the impact of the change in independent variables. So whatever you have done, maybe say a 10 data, if I change to some extent, what will have the results? So that is a very important for us. Again, in the machine learning also we can go ahead with a number of regressions, what we call a linear regression, the way we mentioned the regression, polynomial regression, and like you say the polynomial regression itself is a big domain, a linear is a part of that. We also come up with some sort of a logistic regression, sometimes we call this a classification, not a mathematical regression. So that's possible. However, we have a capital lecture 24, that's the next lecture on the regression and classification algorithm. Will be detailing more about algorithms. Here we are trying to introduce concept and then why we really require it. Now we see that particularly when we have a data, we have thought, or we have trained our maybe thought some model, or we are trying to dig out some model using training set, and then we are doing validation, and then we are doing the testing. But when you go for the training itself, how do we know that our model has been trained properly? Actually, that we require a model parameters, what we give the weights and biases, some constants, and then that need to be updated, and we do iteration. So this is about we have written epoch 100, is means kind of 100 iteration has been done to achieve this kind of results. Here we are trying to give the results from that point of view, right? So in this case a kind of iteration, and then we record iterative loop. We start assuming something and then we do iteration till whatever we have the data available. That means we will be having some inputs and some outputs. Whatever input, it will give me model, and from that model I can predict what will be the output, and I compare output which is already given to me and output which is predicted by the model, and compare, and then we say comparison it is too far, and we need to continuously maybe say iterate it using some algorithm, some optimization algorithm. It can be some sort of cost function which we want to minimize. That's possible, and that will generate a model which will have a minimum variation. So in this case you can see here green, it has a very low variation. So that's why we can say through iteration, after 100 iteration this is the results. We will take one example to demonstrate this thing. Now what is the really quantification method? What do I say convergence? Because most of the numerical method we do integration, or maybe say we do the iterations in a manner, and then finally come up with the results. Either it's a number of iteration, oh after 10,000 iteration whatever comes out I will be happy with that, or it can be, yeah, error can be minimized to 0.1%, 0.01%, 0.001%, those kind of things. So here we use again a statistical method to assess the significance of parameter and overall goodness of it. Here we use a mean squared error, MSE, root mean squared error, and mean absolute error. So three parameters we say that mean square error, root mean square error, and mean absolute error. As far as my knowledge is concerned, mostly people prefer root mean squared error, or MSE. This is a word been preferred compared to other, and then based on that we can be checking. However, we know that this the parameters, this matrix serves a appropriate method to observe what is the output and what is the projected output in this situation. So what we have written MSE in this case is basically average square differences between predicted value and actual values. What is the error coming out of that? I mentioned that our MSE provides a more understandable measure, so that's why it has been utilized extensively. However, if there are outliers of many, then many times we use a MAAE also. That mean absolute error should be highlighted, so that which is a less sensitive, because when you do a squaring they become a little more sensitive, but here we are taking only the absolute value, we are not squaring. So if their outlier are many more, then we try to use MAE, otherwise we will be using RMSE in our case. Now let's take one example. We are talking about linear regression. As I say, the regression also have a many the categories itself. Just to take one example, I picked up from again a literature from IIT Delhi on faculty here. Now what we are saying, there is some output y and some input x. Now here we are assuming some model that h theta x is a function of theta 0, theta 1 into x1, theta 2 and x2. Now here the inputs are x1 and x2, so x1 and x2, and y has to be a function of x1 and x2. Here we are assuming some model is a linear model. This is a constant, and this is a multiplication of x1 and multiplication of x2. It can be vector form. That's why we can write here and then the hypothesis, and in the beginning x0, and here we are taking a number n is a number of input variables, maybe 2, maybe 3, maybe 4, maybe 5. Here in this situation we have considered 2, so it can be the number of input variables. And then we say 0, there is a 0 here, we are using x0 multiplied by x0, that is equal to 1, right? So when we generalize, we do this kind of modeling. Now as I mentioned, that whatever we are estimating, that these values have been given, so what we say, y1 will be given, y2 will be given, y3 will be given, x1 as such, x11 has been given, x12 has been given, x12 has been given, x22 has been given, something like that in this situation. Of course these are not the same, um, just for the purpose. So this value will be given to us, that these are the outputs, and whatever the model H should give us this kind of output to us for the values. So that's why the error function comes. So whatever output we are predicting using this model and what has been given, if they are different, that's the error, and it has been squared, so that penalty goes in a bigger way. And penalty, that means when we do iteration, h theta should be iterated minus, so that finally it comes very close to a yi. Again, this can be only 70% data can be used initially for testing purpose, 20% then validation purpose, and last 10% for testing. So this is for training, this for the validation, and last count 10% can be testing purpose, right? So if the testing and the validation comes the right way, then we can say it can produce in future also. So here now the cost function has been given, and we say number of data samples is a y to m, assuming that it up to the m it has been given here to us. So this has been given. Now when we use some sort of optimization method, here we are using the gradient descent method. You differentiate and find out what will be the values. So you differentiate this value, as such you get this results, and the detail has been given over here why we are getting this kind of relation. It has been given over here. Now here the only one thing which we are trying to introduce, alpha, that's a learning rate. And if you use a gradient descent method, initially alpha will be equal to 1, but we don't want that fast to achieve. So we generally take very low value, alpha can be 0.01. That means we want to gradually move and take steps in a manner so that we get a reliable solution. If you take a 1, that's a real gradient method as such, a kind of mathematical. We already have the rules, or we know the already for the model here. Here we are trying to make a model. We are trying to take a model in the manner and trying to find out what should be theta 0, what should be theta 1, what should be theta 2. That's what we are trying to dig out. So if I already this relation is a firm, already given very right values, then I can choose alpha equal to 1. But when we have a little inaccuracy, we do not know. Initially we assume everything 0, theta 0 is a 0, theta 1 is a 0, theta 2 is a 0. Initially we assume that, and we iterate. And based on iteration, and this is what iterative loop has been given, it can be iterated and come up with the right results. So this iteration may require 1000 iteration, 10,000 iteration. You need to give some sort of accuracy definition. That accuracy or percentage should be lesser than this, then only it will be the completed, or maybe otherwise go for 10,000 iteration. Whatever results comes, we will say it is okay for us. So these are the something which generally when we apply algorithm, we come up with the results. So now just to get the results, we have written a MATLAB code. We say read x, read y, these are two data, this is the output, this is the input. Now we are taking only single variable. Now we are trying to find out number, as I say the input variable is a 1. Initially we are defining theta value, and as I say that learning rate, we are taking very low values, a 0.01. We are defined upper limit of iteration 10,000 as such. Again we can do some convergence criteria, is possible, but initially we are trying to learn, and then we are trying to predict, then we are trying to find out error, and then whatever we learn, how do we go for the modification iteration of the theta. or theta update that has been given. Once it is done, so here there is no convergence criteria has been given. We are trying to do only for 10,000 iteration. Whatever comes out, we will see the results. And then once it happens, then we are trying to plot those things on the x and y label, so that data results come to us. So this is what the MATLAB workspace gives to us, and this is a what we get directly from using this kind of model, right? So this is a what we are writing simple code to get some results, and this is a linear interpolation, and this is a regression line. We are able to see there are some data above, some data below. So this is what we are doing. Again, we are not doing any in this case validation, no testing. That's the initial algorithm just to demonstrate how it really works. Now you go for the data. There are these data. We can say that this is x. That's what we are using the predictor, and this is the y response. There are 100 data has been utilized. So first 20, 1 to 20 has been 1 to 20 has 19 here. 20 has been given here. Then we again started from 21 to 40 here. Then again we started 41 to 60, 81 sorry 61 to 80, and then here 81 to 100. So these data have been given, and these data we are trying to see that how a curve fit method will work, because again MATLAB has a curve fit algorithm. So we have developed our own algorithm, but we are trying to compare with the MATLAB algorithm, because reason being we have given only the training data 100%, while same thing happens into the curve fit method which has been utilized in the MATLABs. So you can look at that we have used the simple MATLAB platform. MATLAB has completely used the word curve fitter. If you type curve fitter, it will ask you the data x and y. We have given the x and y data by just typing on x the prompt command prompt, and then you can see that they have fitted this curve. And of course is a polynomial, single degree polynomial, that is a linear curve, and this is a relation which has been given in this form. You can see the here the what we were thinking about theta 0, and this is what we the theta 1. So theta 0 in this case, theta 1 and theta 0 has turned out to be something like a 0.9903, and then the theta 1 has turned out to be like 0.008. You can see here it gives a very good information whatever the data we were using. That means everything is being governed by the initial data, even it is not a linear, because there is a hardly any fluctuation about this. So this is a very important information when we have a data and somebody says, oh, there is a some linear curve. In my view, there is a linear curve. Most of the time this is a major value, and this is a kind of perturbation, maybe some sort of fluctuation. So this is the real value, and I believe even that this is not a linear relation as such. It's kind of constant. Y is more or less constant, and then if you look at the data, it is the fourth response data is coming 0.9952. Sorry. Yeah, 0.9952, 0.990, 0.997. Question comes, am I really able to measure? Now, suppose there are graphs and I digitize and get this kind of data. Will I really utilize a linear regression algorithm? So, this is important. How do we filter the data? How do we really understand the data and make much more meaningful results out of that? Now, this is what we mentioned. Now we are trying to compare what we have learned from our algorithms. You can see that our algorithm is doing a proper job. It's not really violating too much significantly, and then whatever has been given here more or less coming on here in this case. So this is a really good understanding that how do we use our model in appropriate manner. Now fortunately the MATLAB has brought a new thing what we call a regression learner. And what is that? The regression learner is a tool in training of various regression models. Even the model which we are going to learn in the next lecture, MATLAB has everything available inbuilt, particularly handling pre-processed numerical data set. what we do, we import the data, and after importing data, it's necessary to establish, to figure out, to mention which is a predictor, which is a response, because MATLAB will not be able to know which is the x, which is the y. We need to define it, and this is a kind of in the regression learner. You can see here results are being given. We need to open a new session, import it, and then feature selection, which will be also learn, and we are learning in this case PCA optimizer, training models, and then responses, layouts, generate the model. Everything has been given in our MATLAB. So once pre-processing of the data has been configured, we can go ahead with all the regression models. You can say, yeah, you apply all the regression models. I don't know which regression model is going to fit. It's a linear, it's a polynomial, it's a kind of a neural network. We don't know really which one will really be able to give us good results. So we can do that kind of thing. So now here I brought here, we say one, we compare one decision tree and one linear regression model. So when you train, you can really say that model 1, model 2, model 3, model 4, model 5. We can define, and then the results come something in manner. We can say here these are the true value which are given. They have made a model is a predictive value, and of course if you want error, that also will come. You can see here these are the outliers, and then maybe quite possible this can be eliminated in a model. We say these are the data which are really not required. So when we have a data, at least we can come up with the right results, and we can really check. And here you can see here they have given a RMSE value. If the RMSE value is very low, 0.0017, and here RMSE is further lower, so linear regression is giving much better results, even compared to decision tree. And then of course here we are able to also get MSE and MEA also. So whichever value you want, this and the platform is able to give to values to you. Now here you can see very clearly MSE doesn't have much meaning because 10 to minus 6. Compared to that, RMSE is a much better value which can be incorporated for the feedback loop also when we are trying to improve results. So that's very important to consider. Now coming to the when we are trying to model also error, and then you can see here that outlier, you can see error in this case is very high. So wherever error, and after doing 10,000 iterations, even it's not getting corrected, it's better to remove all this data which are there. Maybe even data are lesser than 5%, or maybe say that we can reject, and we can say these data are not really required, we will go further, or maybe either do a retesting of those data, whatever value we have, and even though we are picking up a full literature, maybe they have done some error in that, and then if we are assuming the model is good, whatever we are done, then it we can correct it according to that. Now coming to the other one model, because you can will find in the literature people use a decision tree. They have used SVM also. We'll be learning in next lecture detail about that. But you can see when we are going for SVM, many people, because when we read the literature, people say SVM is giving the good results. And of course it can give good results, but naturally under which condition, that need to be understood. That's why we really required to learn the algorithm. MATLAB has said we don't have to model. This platform is there, you give input, it will give output to you, but you need to know which method will be more applicable. Of course one is the data and one is the results quantification. Here you can see RMS value is giving worse than even the decision tree in this case. So based on that we can reject, but we need to understand why it is behaving this manner, so that will maybe kind of broaden in a bigger manner. So what we see overall our another suggestion is that employ research learner method tool which is available in MATLAB to train various regression models. It can be linear regression, regression tree, Gaussian processing regression model, support vector, neural network, and then come up with results, and then you say diagnostic metrics such as a model correctness and plots. You try to plot it and then verify it also, and then when you are comparing results, and you select the most suitable model as such in this case, but with understanding. It should not only the mathematical, and that the really the algorithm, maybe this platform is giving some results and just start believing in that. We require little more understanding why it is happening, and that's will really give a more innovativeness to us, more creativity to us to really go for the next level. So this is very important for us to understand and come in a big way. So with this I say thank you for attending this lecture. Thank you.